Hello, good afternoon everyone. Today inshallah we will continue on the vector spaces. I want you to review because our exam, our first midterm, will cover the first three chapters and it will cover almost to the half of chapter 4. I think for up to 4.2, 4.3, we're already covering all of this. I want you to review deeply the propositions. The main thing that you should review in all times, the propositions. So when I am in the matrices or first chapter, should go through the propositions of addition, subtraction, transposition, inversion, multiplication. This is very, very important. This is the places that he will try to ask you about, because he knows that everyone, once he starts solving, he will skip those propositions or he will read them quickly. Okay, do you understand what I'm saying? And he will go to problems. So we usually targeted those propositions. So you will have to study them very well. And I will start with revision on this tomorrow, inshallah. I will start first by the propositions in all our course till till the vector spaces, and also we will go through some problems that target these propositions deeply. Of course, the propositions in determinant also is very, very important. The classification of a system of equations is very important. The link between the rank, the link between the inverse, the adjoint matrix, these parts are really very important. How to get a cofactor, how to get an algebraic complement, what's an Hermitian matrix, all of this is really very important. The idempotent matrices, if you remember, those matrices, once you multiply them itself, it will be the same. I will show you some of the games tomorrow, inshallah, about these questions. Today, let's remember that we are already in the part of vector spaces, and we know that there is some conditions for a bunch of objects or vectors to form a vector space. I will start with the following. Once more, I told you, the first midterm will cover till the mid of vector spaces. So you will have matrices, linear system determinants, and up to 4.3 in vector spaces. This slide is really very important. We already studied it before, and I will repeat it right now as a recap. Let's study it and read it step by step. This is really very important. He is given or starting by let E be a vector space. It's supposed to be at the time being, all of us, nada, know what's a vector space. Do you have a definition of vector space? Do you remember it? It's a group of vectors that admits addition between vectors and also admits the multiplication in a scalar, plus the existence of an origin. That's a vector space. Okay? Of course, with the 10 steps that you should, in all times, test in the addition and the multiplication of the scalar. So, we already know that E is a vector space. See, all of this is done. Okay, over K, and we know what's K. K, it covers the real and the complex plan, Miss Nada. Okay, and U1 up to U are elements of E. So, let's assume that E will be R3. So the bunch of vectors that can generate E or R3 are U1, U2, U3, U4, a bunch of vectors. Are you with me, Fatim? Okay, perfect. We say that V belongs to E is a linear combination of the vectors U1 up to UR. So once more, I have a vector space which is E. This vector space, it contains a bunch of vectors. Those vectors will form this vector space by a linear combination. Ya Faisal, what's a linear combination of a set of vectors? If there are scalars, alpha 1, alpha 2, up to alpha r, once you multiply them by this set of vectors, you will be able to get any vector in this vector space. يبقى تاني مسندة the vector space, we already know what's a vector space. A vector space, it's a bunch of vectors. Those vectors already prove addition and multiplication by scalar. We already done from that. In this vector space, Jana, you have a bunch of vectors, u1, u2, u3, up to ur. It depends on the dimension of your vector space. Those bunch of vectors, I can generate from them each vector in this vector space. يبقى المجموعة دي, I can use those bunch of vectors, use a specific bunch of vectors to build the whole vector space. Do you understand what I'm saying? Okay, how to do it? By making a linear combination. So like, what's a linear combination? A linear combination, it means I will get this set of vectors and I will multiply each one of them in a specific value, which is a number, belongs to real numbers or complex. Once you make this addition, you will have any vector in this vector space. So actually, u1 up to ur, it's like the generators of this vector space. Just with replacing the values of alpha 1, alpha 2, alpha 3, and alpha 4. Of course, this is enormous number of vectors. عدد غير محدود, a huge number, infinite number of vectors. Because don't forget that alpha 1 changes from negative infinity up to positive infinity. Alpha 2 same way like, and the alpha 3 same way like. So it's a huge number of vectors. Okay, once more. We denominate scalars, we denominate the scalars alpha 1, alpha r by coefficients. We call those numbers coefficients. And the order of these values is called a sequence of coefficients. So I have the coefficients and the sequence of coefficients. What the difference between them? The coefficients are the numbers by themselves. But the sequence, which is gonna link alpha 1 in the first vector, alpha 2 in the second vector, and so on, okay? Okay, very good. Let E be a vector space, U up to U are elements of E, the set of all linear combination, all of these linear combinations, all the vectors U1, that's the set, alpha 1, U1, alpha 2, U2, such that from alpha 1 up to alpha R belongs to K. This is exactly what I'm trying to describe to you. That's a huge set. It's an infinite number of vectors on this form. Is a subspace of E? Of course it's a subspace, because each vector space is a subspace from itself, and a vector from itself. A vector space from itself. Okay, U1 up to UR are elements of vector space. We denominate subspaces generated by the sequence U1 by UR by the vector U1 by UR. And they will call them generators of this vector space. So actually, U1, U2, U3, U4 are the generators of this vector space. How to generate vectors? By choosing alpha 1, alpha 2, alpha 3. Once you multiply them together, you will get vectors in this vector space. Okay, this is really very cool. That's the subspace. How it's going to be generated from this, from this set. We call them generators of F by the sequence U1 by UR, and also the sequence of the coefficients alpha 1 by alpha. Examples of subspaces generators. The major one in R3, which is 1 0 0 0 1 0 0 0 1. By using those three vectors, I literally can generate any other vector in R3. Think about any vector that you want to have. 7, 8, and 9, it's easy. If I want to have 7 and 8 and 9, which is a vector in R3, okay, it's really very easy to do. All I have to do is to multiply 7 times 1, 0 and 0. Plus 8 times 0, 1 and 0, plus 9 times 0, 0 and 1. And then I will have the vector, which is 7, 8, and 9. Think about any vector that you want to have, just replacing the values of alpha 1, alpha 2, alpha 3, you will get your vector. So actually, this vector, 7, 8, and 9, is generated from this equivalent form, or from this canonical basis, or this set of vectors, by just choosing alpha 1, alpha 2, alpha 3, and so on. If I want to generate Ziyad, if I want to generate the vector negative 3, 5, and 4, how to do it? All I have to do is just replacing this number by negative 3, replacing that number by 5, replacing that number by 4. So I will get the new vector, which is negative 3, 5, and 4. If I want to have the origin, I can do it. simply by choosing those numbers by 0, 0, and 0. And then I will have the origin of this vector space. That's simply what have been said in the previous vectors, in the previous two slides. Okay, those are generators of this vector space. There is some spaces I will put extra information, as you will see down the road. Okay, let's look to this one. This is Kn, which means it can form R4, R6, R7, R8. Ziad, انت عارف يعني R8? Do you know what's R8? R8, it means the set of vectors which contains 8 components. That's R8. Okay? So you will have 8 components. طيب يا فاتن, ال 8 components دول, how to generate them? By choosing 1, 7 zeros, 0, 1, and 5 zeros. احنا قلنا R7, R6, يبقى 0, 1, and 4 zeros. Okay? And so on. So each time I will move positive 1 to one direction. This is gonna be the generators of this 6 by 6 vector spaces, or R6 or R8 or R7 or whatever. Okay, the general form is exactly as you can see. It's explained here that E sub I belongs to Kn, which means it's a form with the same dimension that you are using. Okay, those nubles or these vectors, it's exactly in this shape. So you will find components equal to 0 except the ith row. So the first row will be 1 plus zeros. The second will be 0, 1, and zeros. The third one will be 0, 0, 1, then zeros, and so on. That's the canonical form for Rn. Okay. For any U1, UR vectors of vector space, I can generate the origin. Okay, simply by choosing alpha like zeros, as we saw. Okay, also for an M by N K, for any set of matrices, it can actually do a vector space. Let's say I'm seeking the vector space, Miss Fated, I'm seeking the vector space of the matrices 2 by 3. What's gonna be 2 by 3, Miss Nada? 2 by 3 are those type of matrices which contains A, B, C, D, E, and F, which is simply 2 by 3, 2 rows and 3 columns. I can generate them from a set of objects or a set of matrices, exactly the same. And it will be on this form. Look to that set of matrices. It can be 1, 0, 0, 0, 0, 0. The second one will be 0, 1, 0, then 0, 0, 0. The third one will be exactly 0, 0, 1, and zeros. The other one will be 1, 0, 0, 0, 0, 0. And there is also more of them. Okay? Also, I will need 0, 0, and 0, 0, 1, and 0. Okay? And the last one will be 0, 0, 0, 0, 0, 1. Okay? That's the set. That's the set of matrices that can generate this vector space. I can generate any matrix, 2 by 3, using this set. Simply, if I want to write it as a linear combination, this is going to be times A plus times B plus times C plus times D plus times E plus times F, and I will be able to get this matrix. Okay, so it's really very simple to find the generators of each vector space and explain it, and it makes really very good sense. Okay, so this is for R3, that's for Kn. Those are for the K matrices, and it's explained exactly as I told you, where Eij is the matrix of M of dimension M by N with all positions zeros except the position I and J, which is equal to I. That's the description of the system that we saw. Okay. Also, this guy, it can generate, or this problem, Ms. Nada, it can generate a specific the description given here, it can generate a specific sub-vector space from R3. Let's read it together. You want you to form ABC belongs to R cubed. So I will have a vectors which contains three components, such that the first component is equal to 2b plus c. So how to find this set of vectors? Listen, the first step to do is to use this relation and to make a substitution. If I did this, say that it's gonna be a 2 of a b plus c, then b, then c. That's the form of these vectors. The form of these vectors, I can divide it into two vectors based on the various variables that exist in this vector. بص كده لسنا, it's exactly the same like 2b and b and 0. Then I will add c and 0 and c. If I added these two vectors together, it will give me this vector space, okay? Or it will give me the shape of the main vector. Look, c plus 2b, this is the first component. 0 plus b, it will give you the second component. And the c plus 0, it will give you the last one. Also, so I can take c as a common, which is a number. That means I will have 1, 0, and 1. Am I right? And I can take also b as a common. If I took Jana b as a common, I will have 2, 1, and 0, which is actually a form of a linear combination misfitted, especially for b and the c belongs to R. So the set that generates this vector space is simply the vector 2, 1, 0 and the vector 1, 0, and 1. This set of vectors can generate this F, subspace of R3. Think about anything that you want to form. It will be on this form. Using just only these two main vectors. If I want to perform thus this vector or the main vector, it's easy. All I have to do is to make a linear combination from these two guys by multiplying the first one by b and the second one by a. And I will have the form that I want for expressing this sub-vector space. Okay? Of course, if alpha and beta are zeros, you will have your origin. And of course, if you add any two vectors on this form on each other, you will get exactly the third one or the result approving this relation. معايا جنى? Okay. Any problem? This is very major. This is very, very important. How to generate a set of vectors that will represent a certain sub-vector space. It's really very easy. Look to the variables. First thing, make the substitution. So see what's the components, how the components are arranged. The components are arranged. The first component, it's a multiple of the second and third. Then do your, make your substitution. Then start to separate them. Then start to take common. Of course, the common values belongs to R as yet. C will be belongs to R. So it will give you from negative infinity up to positive infinity. And those are the core, the main generators of this sub-vector space. تفضل.
مفيش طريقة طب أعرف أجيبها الأسد؟
إيه؟
مفيش طريقة معينة.
هي دي الطريقة الأساسية. تعمل substitution، بعدين تبدأ تبص على الفاريبلز وتبعدهم عن بعض عشان تقدر تطلع فيكتور بفيكتور. There is no other way. Okay? Especially that you have an infinite number of vectors that can generate any vector space or sub-vector space. This is why we will see down the road what's called a basis or a span of vectors. Those definitions, we'll see them down the road. But for the time being, this is really very, this is fair enough. So I replace the a by 2b plus c as I told you, taking b and c as a common. As you can see, it's a linear combination. That vector can be generated from those two guys. Okay, so if I'm removing B and C, which is the sequence of the coefficients, I will have the generators of this subvector space in specific. Here is some problems. I would recommend that you go through the problems. Already I've sent you the exercise book previously on the WhatsApp. And it really exists on model in the resources. This part is really very nice. Consider E equal to R squared, which means we are talking about a vector space in R2. So it has two components, all the vectors, two components. And define addition and scalar multiplication as follows. خلي بالك يا فاتن انا هعرف الاديشن باسلوب والمالتيبليكيشن بسكالر باسلوب. بصي على الاديشن يا ندى. لما ببص على الاديشن A1, A2, B1, B2, it's normal addition. You are adding the first component together, the second component together. Remark, I can replace them, say that. This is, I'm telling you how it's gonna be done. So the addition in this problem will be the normal one, that you know. But in multiplication and scalar, Miss Fatin, it's gonna be different. If I have any vector, A1 and A2, and I'm going to multiply by alpha, see what's gonna be the result. The result is gonna be alpha times A1 and 0. So it's not just a multiplication in a scalar. I know Miss Seda that once you have a vector and you multiply in a scalar, the scalar value will be multiplied in all the elements, in all the coordinates. No, I'm changing the condition for here. For this particular vector space, the multiplication by scalar will lead to that this value will be multiplied by the first component, and the second component will be 0. This is the changed type of this dot multiplication. That's the definition of it. Do you read me? فاهمني؟ اوكي. يعني دي القاعدة اللي أنا هحطها للضرب في رقم. الضرب في رقم في أي فيكتور بضرب الرقم في كل الكومبوننتس. هنا بقى بالتحديد أنا لا هشيل اللعبة. لما اجي اضرب اعمل multiplication by a number, once you try to multiply by a scalar, it will be multiplied in the first component only. The second will be 0. Okay. For all A1, A2, B1, B2 belongs to R2, and بص بيكمل عليك اهو. And all scalar belongs to me to R, to all the set of real numbers. يقول لك وريني ان R square with the addition and the multiplication with the scalar is not a real vector space. ده ما هوش real vector space. تفتكر علشان approve ان هو in order to prove that's a vector space, how many conditions I should satisfy? Actually, there are 2 rules, but it contains 10 points had to be checked. Okay, let's do them one by one. Remember that if I have for the addition, it is all applicable. For the addition, it's all applicable. If I have a vector A1, A2, B1, B2, and added them together, the result will be a vector in 2 by 2. If I'm checking the distributive property, it will be applicable. The commutativity, it will be applicable. Multiplication existence of a 0 already applicable. Negative existence of a negative value already exists in the addition. Let's go to the multiplication by scalar, because the major thing that I change in Jana in the multiplication by scalar. Okay? If I have a value multiplied by V, it's going to be multiplied by the components, it's okay. If I have alpha multiplied by A, it will be multiplied also, there's no problem. It can be distributed, no problem. Can be distributed 2 constants times V, will be no problem. But can you please, Ms. Seda, check this property? If this property makes sense, the multiplication by an identity. If I multiplied by identity, the definition in the scalar multiplication, it will reserve the original thing. So, if I multiplied the vectors E1 and E2 in 1, I should have E1 and E2. But instead of having this guy, I will have, through to this property, A1 and 0, which doesn't equal to the original value. Once more, For this specific property, there exists one, which is the identity for multiplication in a number. 1 belongs to V, such that 1 times V is equal to V. Here, if I try to multiply 1 times A1 and A2, I will have A1 and 0 instead of having A1 and the mean and the A2. And any failure of any of these conditions will lead to that you don't have a vector space or a sub-vector space. This is why it's not going to be applicable. I've already wrote it for you, so it is easy to show that it fails one of the vector space axioms, as you saw, the scalar identity axiom. All the rest of the axioms are okay, and this is very, very interesting. If you multiply alpha, A1 and A2, the result is going to be alpha A1 and 0. And so if you choose 1, as I told you, instead of having A1 and A2, you will have A1 and 0, which means it's not equal to the original value. So that means it's failing to get the main vector that you are using, and so it's a failure in this subvector space. Okay, for each of the following vector spaces, indicate the element 0. فؤاد عايز اجيب الاليمنت زي فيصل اسف. هو فؤاد راح فين؟ بقالي مرتين ما شفتوش. فريدة. يا دنيا. ايه صح؟ فريد فين؟ ما حدش يعرف فريد فين؟ اختفى يعني؟ هو شكله فيه حاجة. طيب بيقول for each of the following vector spaces. وفين عمرو؟ برضه عمرو يعني ايه كل سنه طيب؟ اري جورج يعني مهاب نقل هو كمان؟ من امتى؟ مين قال لك ده بتعمل اشاعه؟ انا فرانشيسكو ما عنديش. طيب بيقول for each of the following اللي بتكلم في ده بعدين. For each of the following vector spaces indicate the element 0. Indicate the element 0. طبعا in E belongs to R4 for this vector space. So like, do you know the origin, how it's going to be? The origin. This is R4, the origin. Yes, you are correct. 0, 0, 0, 0. صح? Okay, for this one, I'm talking about the origin. This is really very simple. The origin for the first one is 0, 0, 0, and 0. The second one, it will be a 2 by 3 matrix. So it's going to be زيادة. For number C, this is the origin. For 2 by 3. This is the origin for R3 of X. انت عارف يعني ايه R3 of X؟ A polynomial third degree. طيب يبقى شكلها عامل ازاي؟ هيبقى 0 x cube plus 0 over x squared plus 0 over x plus 0. That's the origin of this guy, which is equal to, which is gonna be 0, the set of 0. Okay, state the opposite for addition of each element of these vector spaces. What's the inverse of the addition? This is gonna be -1, +2, -3, and 0. This is gonna be exactly the same. معايا say that. This is gonna be -1, +2, -3, and 0. Okay, for this guy, it's going to be -x cubed plus 2x squared -3x. Okay.
ليه مش الثالث ما بيبقاش بطريقه
طريقه ايه؟
هي الخلطه بتاعها
لان دي حاجه ودي حاجه. مش فاهم ايه دخل ايه اللي دخل انت بتقوله في ده؟
هو مش عايز الانفرس بتاع السي.
لا هو عايز هنا the opposite for addition for each vector. The opposite of addition. Okay. هنا بيقول determine which of the following sets are subspaces of the corresponding vector space. Please think. Please think. This set F1, which is the set of all vectors A and B, belongs to R squared. Like, what's the description, Jana, of A and B? The description is that A is greater than or equal to what? To 0. 10. هل ده بيريبريزنت سب سبيس اوف ار 2؟ ها طب مش فكر ليه؟
عشان في اوريجين.
عشان في ايه؟
في اوريجين.
ماشي في الاوريجن هو ام اي ايكوال تو 0. This is number 1. number 2
والرولين مطبقين.
الرولين مطبقين. Are you sure? Are you sure? So it's stating that all A belongs to R, all the numbers. But A should be greater than or equal to 0. So if the 10 options already exist, I will write them for you. Okay, let's say. Those are the main options or the main propositions. But don't forget, in this addition, you have multiple choices or multiple axioms. And in the scalar multiplication, there is also axioms. Just please do think. In the addition, I have the existence of the opposite vectors. The opposite of an addition. Once you add them together, you will get the origin. The question is, if this guy is multiplied for this 4, if it is multiplied by a negative value, negative 1, it's going to be negative A, which breaks this condition. Am I right? So it's not a subvector space. Those are the conditions. F is a subset of E. This is satisfied if contains 2 coordinates, and the E is R2, which is the set of all coordinates, 2 coordinates. Okay, 0 existence as exactly as he had said. Okay, in the addition and in the multiplication of the scalar, you should think a little bit. So a subspace must be closed under scalar multiplication. So for a vector with 1 and 0 belongs to F1, and the 4 lambda equal to negative 1, if I multiply by negative 1, then the value will be negative 1 and 0. And negative 1 and 0 on this form satisfy this condition. Yeah, this is not. This is why it's not a subspace. This set of vectors in R3 does it represent a subvector space? This just only set. Those set. خلي بالك سوري دول مش generators. Number B. Those are not generators. لا. This is the set يا فاتن of how many vectors? 3 vectors. Are they closed under the addition or multiplication by scalar? They are 3. The origin exists.
Yes.
The origin exists. Okay, so this condition is satisfied. But if I multiplied any of these vectors by a scalar value, then the result gonna be within the set. يعني لو انا multiply by half, هل الفيكتور 0 half and 0 one of these vectors? It is a specific set. انت معايا فيصل؟ يعني دي مش set مش generators. generators vectors لو انت عملت فيهم multiplication by scalar هيجي لك new vector. بس اللي موجود قدامي ده it's a brackets of a set. So actually the total number of vectors are how many vectors? Are 3. هل الثلاثة vectors دول represent؟ لا. لأن لو أنت جيت تعمل لهم multiplication by scalar it will be other vectors. Okay? I've already wrote that also for you. So these 3 vectors, a subspace must be closed under scalar multiplication. Take W0, 1 and 0, and if you choose lambda equal to half or 2 or 3, it's going to be another vector which doesn't belong to this one. If not, F2 is not closed under scalar and it's not a subspace equivalently to the space of 0, 1, 0 is infinite, while F2 connects only 3 vectors as I told you. This problem is really very good. We need to solve it together. Nada and Fadden, please leave your cell phones. Consider the sequence. Now, I'm not giving you 3 vectors, Sulay. I'm giving you a sequence of vectors that can generate a subvector space or a vector space. So he's telling you, consider the sequence. This is the sequence, which is 1, 0, 1, 0, 1, 1, 2, negative 1, and 1. And he asked you, indicate whether 1, negative 1 and 2 is a linear combination of those vectors or not. How to do it? Fadden, how to do it? قول.
اعمل augmented matrix.
هعمل augmented matrix عشان بعمل ايه؟ كلامك صح مليون في المية.
هجيب الثلاثة.
ايوه اروح قايل ايوه يا زياد صح alpha 1 times 1, 0, and 1 plus alpha 2 times 0, 1, and 1 plus alpha 3 times 2, negative 1, and positive 1. And those values of alpha 1, alpha 2, alpha 3 should generate this vector space, which is 1, negative 1, and 2. So, بالفعل, I will solve a system of equations in order to determine the values of alpha 1, alpha 2, and the alpha 3. This is very, very simple to do. معايا فيصل؟ هعمله ازاي؟ اهو. The values will be 1, 0, 1 and will equal to 1. For the second row, this is, this is the values for the first column, which is going to be 1, okay, 1, 0, 1, I'm sorry. And for alpha 2, it's going to be the 0, double 1. And for the third one, it's 2, negative 1, and 1. And the results will be 1, negative 1, and 2. Then I will try to solve in order to get the values of alpha 1, alpha 2, alpha 3. This is alpha 1, which is, as I told you, 1, 0, 1. And for alpha 2, it is 0, double 1. For alpha 3, 2, negative 1, and 1. The first step will be, any ideas? The first step?
0.
This is going to be 1, 0, and 2. And this is going to be a 1. I will multiply the first row by negative 1 and add it on the last row. So negative 1 plus 1 is going to be 0. Negative 0 plus 1, it is 1. Negative 2 plus 1, it's negative 1. Negative times 1 with 2, it's going to be positive 1. For the second row, it's 0, 1, negative 1, 0, 1, negative 1, and negative 1. Okay? So we multiply the first row negative and add it on the last row. Negative 1 plus 1 is equal to 0. Negative times 0 plus 1. Negative 2 plus 1 is going to be negative 1. Negative 1 plus 2 is positive 1. Then I will start to add them together. Okay? I will continue for the second row. So the second row will be 1, 0, and 2. This is 1. I will multiply the second row. I will leave it as